We'll begin in a few short minutes. Let the time for people to get in. In the meantime, do any of you have any questions like related to pretty much? Well, we're going to cover Structs today, but it's pretty much relevant for the assignment. So, do you have any questions regarding this assignment? Right. Listen, a few more minutes then. All right, everybody. I think we have enough people to start. In any case, this is recorded, so the rest are going to watch online later on. So today we'll be covering Struct. I'm pretty sure you're all familiar with that, but more specifically, we're going to cover more advanced topics of Structs as your assignment is going to need it. You're probably going to be able to get away with simpler Structs, but if you take the time to make more complex structures, it's going to be easier for you in the long run, right? So we're going to start pretty easy with just a basic struct here, just to get everyone on the same page. So the way to define a struct, right, is simply with the keyword struct here. And here I've defined multiple variables. So you can think of it as a class. In fact, yeah, the only difference between a class and a struct, and here we're talking C++ because a class doesn't exist in C, is that the struct, all of its component variables are public by default. So if you were to use a struct in C++, all the variables inside of it would be public, whereas a class, there is absolutely no difference, except that all the variables are private by default. All right, but here everything is public. All right, so it's just a container to encapsulate your variables. Okay, so you could put pretty much anything in it: an integer, a float, a char array of a fixed length here, and a char pointer. Okay. So the way I instantiate it, I'll remove this. Okay. So one way to call it, if I were to define a variable of my class or my struct, so to speak, so I would just type struct hello again. So yeah, you're not going to get away with typing struct. So you have to type it every time, unless you do a type def, I believe. So you call it struct hello like this. And then the name of the variable. Okay, so this is just a keyword struct, then the name, the type of the struct here, and the name of your variable, right? So here, everything is undefined. And what you could do is just do h dot a, for example, equal, okay, what else? Yeah, float, so h dot b equals 0.1 f because it's a float. And okay, a char array. So the char array is pretty easy to do. It's h.c equals, and then you could just set it like that. Hello. Right. Actually, you know what? I'm not sure. Actually, for h.c, it's here to initiate the char array. We're gonna need to copy it. Okay, so it's a bit of a catch, and you kind of see here that it's highlighted in red. So this is not gonna work because here it's an object right here. So and this would be a pointer, but we're going to need to copy it. So the one way to do it is just to type string copy like this. And then it would be like the destination is h.c and the content source to destination. So source, okay. That would be hello like this. Hello h.c. So it's copying hello inside h.c, right? And finally, this one, the char pointer array. This one, I believe we could just do it like that. World. Okay. Actually, no. Oh, h.d. Sorry. All right. So tricky difference when it's a char with a fixed length here, you have to copy the string. And when it's a char pointer, just saying equal this will lead to a char pointer. All right. Have any question? I know. And if you're unsure, you can just try it out. If it doesn't work, just try it the other way, right? So in order to see the result, I guess we could just printf the content. And we're going to try to print hello world. So that would be a string and another string. Oops. And then h.c, h.d, right? I'll just make a new line. Okay. Finally, I'm going to return 0. Okay, so this should work. Compile, just do GCC. I think I called it one hello. Okay. Interesting. Address boundary error. What did I do? h.c, h.d. Perhaps I did a mistake here in the string copy. A, B, C, D, and A, B, C, D. What? I'm not sure. Not in this case. Let me just take a look. We'll go back because I practiced it earlier and okay. Okay. So yeah, I did my string copy in the opposite way. So it was supposed to be the other way around. Here you see I did hello and h.c. It's actually h.c hello. H.c and hello here. I don't know what the S is for. Okay, so that works. And finally, h.d equals world, right? Printf that h.c, h.d. Okay, so now it works. I just forgot the backslash n. Um, okay, so here we have a hello world, right? And to answer your question, okay, so if you type man string copy inside of Linux, you should have it. So he copies the string pointer, including the null, the terminating null byte. So yes, it does it for you. You don't have to worry about it. Okay. Most of the string str functions, they're going to include the null character by default. Okay. And of course, the way I did it, I mean, it's not the cleanest way in the world. So another way to do it would be hello.h equals, and then you would have these brackets, and to be more like C friendly, we're going to do it this way. And you could do it like this. You could do dot A equals 10, comma, dot B equals 0.1 float, dot C. So the C one was the pointer, right? So we're going to do the string copy again. String copy dot C. I'm actually I'm not sure it's going to work. It would be a bit weird. I mean, I'm going to try it out, but I don't think this one is going to work. Haven't tried it before. This is some weird syntax. And world. Yeah, definitely that doesn't work. Okay. And then a comma at a semicolon at the end. Okay. I have no guarantee that this is going to work, but let's try it out anyway. Okay. Okay, I had some warning. Okay, what char from char pointer makes integer from pointer without a cast. Oh, you're right. Yeah. It's also a valid way to do it without the variable name. But usually you don't do both at once, okay? You do one or the other, but again, okay, so GCC LSC, those are warnings. So it compiled, but I'm not sure it's gonna, it actually did work. Although with some garbage here, but don't do that for this instance. So here we would do it differently. One way could be with positional arguments. Instead of naming like variables, you could just do them in order. So if I define A, B, C, D, the first one is 10, like this. The second is a float, so 0.0f. The third is the string copy. Still not sure how it's going to work, but yeah. And then and finally world. Okay, so as you can see, we have some kind of garbage. So I would not recommend doing it this way if you are to do string copy in the middle. You could just do it the way I did it the first time, which is like initializing it and calling each argument separately instead of calling it in one batch. But if those were integers, just simple integers, you would have no problem calling it like this. Okay, it's just multiple syntax. Yes.
Another question, why don't we have to like allocate?
So the string copy So, okay,
No, but,
we're gonna need to allocate some memory at the end, but here. So this is a char array of 16. So allocating memory would be doing it in a dynamic way, okay? And structs, as you're gonna see, are not dynamic by default, okay? They're processed at compile time. Their memory, you know, are so they're considered as local variable and not on their heap. Okay, they're on the stack. However, you can have pointers. So like this. So this one would need to be allocated, right? Or you just need an address. And when we define the constant of a char array, it's char array pointer that is returned. Okay. So it's passed here. So that's why you don't need to allocate memory. But looking back at string copy, what does it do? It returns a pointer to the destination string. Okay. So there's a pointer that's created somewhere. And yeah, it's large enough. Oh yeah, the reason we didn't need to allocate memory was, well, simply because the first one was a fixed char array, and the second one is an address that's defined by the constant. So most of it was assigned at compile time and not at runtime, all right? But we're gonna get there. Any other questions? It's gonna go more complicated from that point on. Okay, size up. So size up is a utility function that returns the size of an object, right? And you might have to, you know, play around with it when debugging to make sure that your struct is the right size. And the only thing that you need to know about size up really is the way, you know, you think if you know, for example, that one char is 1 byte and you have 3 chars in struct, how big, what is going to be the size of the struct in your opinion? How big is it going to be? You only in your struct, you only have 3 chars. So it should be at least 3 bytes, right? However, well, your struct in and of itself is going to take some place, right? Some bytes. So I think, is it 2? Stack is used. Okay. Stack versus heap. Everybody know the difference between stack versus heap, right? Stack is local variables. Heap is dynamic memory, the malloc. And inside of cage, the real page, not the page that you're going to design. Although yours actually resembled that a little bit. You would have a separation for the part of it that's the stack and the heap, right? Don't remember which one's on top of which. Let's say the heap is on top of the stack, but I could be wrong. And you would have the stack here, okay? And yeah, but this can potentially grow, but we'll do that later. In this case, it will be page forward. Okay. So stack versus heap and size up. Okay. So here we have an example of size up, right? We have an integer, we have a char name. So char name 10. So it's an array that's 10 bytes long, and float, an array of floats that's 100 items long. Although we have an integer here length. So what's going to be this? So how big is a float? Do you know that? It's like a midterm question kind of thing. What's the size of a float? 4. Yes. I think it can be even larger, but let's go with 4. So just the array of 100 floats would be 400, right? It would be 400 items. Oh, it's in the slides. 400 items. Then we have, okay, so 410. And then how big is an int? The size of an int. Yeah. So 414, could that be a thing? So we would have 414. So let's try to reproduce this experiment here. Vectors over there. Yeah. So I think I coded it already. Although I did not print the size of. Okay. So I'm just gonna print out the size of. I'm gonna print it as an integer, but a size of object is actually an unsigned long integer. So I'm just going to cast it to int, and it's going to be size of the simple vector. Okay. The end size of vector. Okay. Simple vector. I'm just going to pass the variable. What? Yeah, the variable s, for example. GCC. Okay. So we calculated that if we had 400 for the vector, for the not the vector, but the array of float, plus 10 here, so that's 410 plus what's it called? Where is it? Here. So 400, 410, and 414. However, we have 416 here. Do any of you know why it's 416? Yeah. So the solution, I mean, the answer to that is, it's actually because accessing memory by intervals of 4 is actually much faster for the OS than if it were unaligned. So by aligning memory, we're going to add a buffer, and it's always going to be a multiple of 4, okay, no matter what you do. And an interesting thing to note is that, let's say you define a Boolean, right? And C, I believe Boolean exists. How big is a Boolean? It's 1 byte, right? Well, it could even be like 1 bit even. But the thing is, it's actually 4 bytes because we align memory. So it's padded with useless stuff just to fit it into 4. So if you are to use like a Boolean, like in industry, for like C programmers, you would see them using int instead of like bool, because an integer, it's 4 bytes, even though we also know that Boolean will take 4 bytes. So for them, they just use integers. All right. So even though it could fit in 1 bit, it's padded to fit to 4. Okay. So this is why this is 416. It's always going to be padded to fit exactly into 4 bytes, multiple. All right. So just one thing to note. Okay. So if you are ever debugging something and saying, okay, but I don't know why my string is so big, or I mean, it's going to be off by 3 or by 4 tops, actually by 3 tops. Anyway, so just a random fact. Okay. So I think we covered the size of. Let's go with the things changing. Okay. See. Full, okay. And one thing to note is that I'm talking about padding memory, but some OS don't do that, okay? They don't support that at all. But as a general rule, just pretend they do, okay? And you have yet to see like unpadded like memory. Maybe you can disable it in the C program, but your code is going to be much slower. KY padding, yeah. Loads and store are actually faster for existing hardware. It's just hardware thing. Okay, so struct initialization, we talked about this already. So this is the simple vector. As you can see, it doesn't have any like pointers where you need to string copy. So the example that I tried earlier would actually work. So this is the way to initialize a struct with the dots in between here. So by naming it this way, you could actually change the order because you declare the variable name and then its value. So there's no confusion here. But if you were to do it the other way, like this way, here you would have to follow the structure that was already established by the definition of the struct over there, right? So in char flow, okay? You cannot obviously mess it up here, okay? So it's kind of a bit like Java or in Python when you have a function and in the argument function, you pass it either by naming the variable equal to or with positional arguments first, second, third, and so on. All right. Anyone has questions regarding this? Okay. Okay, so what if we wanted dynamic length vectors, right? So what if we wanted to allocate memory? You're probably going to need this for the assignment. So it's absolutely okay to, define pointers here. And as long as you allocate them somewhere and send the address to struct, there is absolutely no problem. Just remember that for every allocation of memory that you do, you need to free that memory afterward. Otherwise, you will have memory leaks, and you might not want that. And especially since you're going to be graded on memory leaks, we have unit tests that test for memory leaks. So you're going to lose marks if you forget to free memory. Anyone like is used to Valgrind, right? No. Okay. So we're going to do this, and I'm going to create a new file. And let's allocate memory. Okay. I'll call it memory.c. What? This story, yeah, it wasn't made by me, it was made by another TA. I guess the prof is going to share you the slides and the recording of this. Yeah. But Valgrind, if it was a tutorial, I mean, it wasn't covered in here, but it's pretty simple to use. I'll show you. Okay. Okay, so let's have a dynamic vector. Where is it? Here. So struct, I'll call it dynamic vector. Okay. So it's a char array of how should we call it? How did it call it over there? Okay, a char array of name and a float. Okay, so this is just for the name function and an array of int. So actually, yeah, they did float. I'll do int. So data. And we always keep length. Okay. Since it's a dynamic vector here, we don't really know where the vector ends, okay? And if you try doing this on your own, you might end up with a lot of garbage. If you see garbage in the output or segmentation fault, it might be because you're trying to access memory that you have no right to. So unless you define an and to your vector, a good way to do it is just defining a length, right? And so here you have a pointer to data, okay? So it's a pointer to integers, so it's gonna make a jump of 4 bytes, for example. And so in your for loop, you could just do for, move the pointer like 4 bytes at a time, and then until the length is reached. Okay, so always good to have that length variable here. I think you had to do it in assignment 1 at some point to parse the input, right? Somewhere along the lines you needed to, or perhaps you got away with it, but okay. So we have our memory here, and it's time now to allocate our structure, right? So you all know what pointers are, okay? This just returns an address to, if it's a char array name, it's just gonna say, this is the first address where the data begins, right? So you would have vector here, and hopefully if you have a /0 or no termination character, you know, stop looking, right? Or you could also keep a length variable to make sure you never go past this character, because after that, the memory might not even be allocated to you. Okay. So yeah, and the float data, it's again another pointer where one float begins, and then 4 bytes later, there's another one, and so on and so forth, right? So let's see how it looks in the code. So we're gonna int main a function here, and inside of that function, I'm just calling the struct dynamic. Struct dynamic vector. I'm calling this D, okay? And then to allocate the length, okay, the length actually is not a pointer, so let's say D dot length. Actually, we don't need that yet. So we could just do D dot here name equals and hello. Again, earlier today we did that with world actually. If you recall, this is the same thing as we saw the first time. This returns a pointer, a const pointer, okay? So this is done at compile time. So it will not be on the heap, it will be on the stacks. It's constant and it never changed. So this will point to an address somewhere in memory, and this will just store that address, right? However, for the data part, we have no guarantee we have no way to know how long it's going to be, right? I mean, of course we could set it, but one way to do it here, dv data, see, dv.data, d.data, it's just to memory alloc. So malloc, and then what you would do is, how big is a float? Because we don't remember, right? How big is a float? Size of float. And if you were to have, for example, 100 elements in it, so you just allocated right here 100 element in memory, okay? So that address space will be allocated for you, and the moment you don't need it, you free that memory, okay? It's very important to free it, and we're going to see why in a short bit, okay? And then I guess in length, d dot length, I could just say 100, okay? Okay. So is everything correct here? Do you see any problem with this code? At the exception that I did not free memory yet. Just ignore that part. What could go wrong in this code right here? Any idea? Good. So let's do printf. We said it was an array of integers. Oh, I said size of float. Yeah, that's not gonna work. I mean, that would work, but printf. Okay. So I'm gonna printf an inch, right? So a digit, and I'm gonna do d dot data, and I'm gonna take the first element. How about that? Actually the 50th. Let's go with that. 50th element is, okay, I'm just gonna do \n. Oops. And then return 0. Okay. Okay. I'm just gonna include the usual stuff, just so the compiler doesn't complain. It would just show up as warning, but so GCC3, right? Memory. Okay, so everything worked out. So 50th element is 0. So we actually got lucky because we define an array of int. So by default, it's initialized for us to 0. So we're lucky, right? If you were to initialize it to an array of some weird objects like structs, okay, you would have garbage because there would be no way to initialize it. So sometimes after I'm allocating memory, you might need to, and this behavior is undefined because you don't know what's at that memory. Sometimes it's going to work, sometimes it might not. But for integers, it's pretty safe, I believe. Okay. So we allocated our memory here, and let's talk about memory leaks now. Okay. So one way to check for memory leaks is to use this program called Valgrind. It's for Linux, of course. But inside the Docker, let's hope it's installed, or if not, just apt install Valgrind. Okay. And what you do is just you type Valgrind and the name of your executable. Okay. And what it's going to do is it's going to run your executable as it, as normally, and it will check for the number of memory allocations and memory liberation, so free. So it will just match the count. So let's run this and see what it does. 8 out of house, right? Okay. So okay, so I have use of an initialized value of size 8. Where could that be? Printf, okay. Yeah, so I got an error that I have an uninitialized value of size 8 because it is true. I did not initialize my int, but I didn't know it was size 8. It's kind of weird. Okay, so blah blah blah. Okay, so what you're most interested is after that. I'm going to keep summary here. So in use at exit, we have 400 bytes in one blocks. We have 2 allocs, 1 free, and okay, so this is the number of bytes allocated, and the leak is 400 bytes in one block. Okay, so and where does the 400 bytes come from? Well, it comes from our array that we defined right here, which is 100 elements long of times 4, so 400 bytes. Okay, this one, yeah. So this is we never freed that memory. Okay, and so we're going to need to free it at some point. So anybody know how to free memory like this? Yes, it is. Absolutely. And for some more complex case, sometimes you need to free each element before you free the pointers. But in our case, I think let's try with just freeing the pointer. If that doesn't work since it's all integers, I think it's okay. Free, what's it called? D.data. Yeah, right. So if we were to allocate dynamically our variable here, if this were to be a struct pointer, a pointer to a struct, we would need to free each element of that struct before freeing the struct itself. Okay, because that would be right now it's not a pointer. Okay, it's a local variable. Okay? But if it were a pointer, you'd have an allocation of memory for that and an allocation of memory for everything inside of it. So you free the inside and the outside at the end. But in our case, just that will work, right? So let's see if it works now. Okay, so now that we freed memory, we see that in use at exit, in use at exit, so what part of the memory are you still using after exiting the program? So we had two allocation, two frees, and what you need to look out for is all key blocks were freed, no leaks are possible. So if you see this line, this means everything is perfect. Okay. So yeah, and there are actually more allocs than you were aware of, and that's okay. If they were not made by you, they're probably being freed dynamically. So probably this here would be the coins pointer might be freed automatically, and stuff like that. Okay. Any questions about that? It's very important that you keep in mind always free memory. If you see malloc, you should see a free somewhere else, okay? And try doing it at the same time and not, okay, I'll write the entire code and then, oh, but I need to check for memory leaks. And then it's a lot harder to remember what frees what, right? Hey, where are we on the slides? Any questions so far? Yeah, go ahead. So what could happen is that you close the software and you still have memory. And because somebody else can use it. And that could be problematic. You don't want your memory. You see the segmentation fault that you get. It's when you're trying to read memory that does not belong to the program that's using. And so it's not in the same, think of that page, okay? That page is a segment, okay? And when you go outside that segment, it's what we call a segmentation fault because that segment belongs to another program which you have no access to. So that's what we call a segmentation fault. So same thing when you go beyond the pointer because it was not allocated. So yeah. And if you terminate the program, the memory is still hanging around and you have not liberated it. So it's going to take more memory in the system because no other program is going to be able to use that memory because it's allocated. So it's going to hang around in the system and some applications are actually full of memory leaks and it just takes more resources. So if you have memory leaks on a cell phone, it's going to result in more battery usage or that kind of stuff. So any other questions?
Yeah, another question. Is it possible to like not use dynamic allocation and stuff like that?
Hardly. That would come from the GCC or the compiler itself. So no, I wouldn't say so. I mean, it could happen, but never seen this before. So yeah. Let's look at that. Okay. So just make sure when you allocating memory to free it. And yeah, sometimes it could happen because you were not aware of it. Some of the string functions like I think str, is it like this, man string dop? Okay, this one. Okay, this utility function, so it returns a pointer to a new string, which is a duplicate of the string s. Okay, okay, so you have a string, okay, and it's all fine. But since you wanna, let's say that string was defined in the main function and you want to use it in the struct, but you pass it by value, so and not by address. So it's a copy. String dot here duplicate would do the trick, but it says here memory for the new string is obtained with malloc and can be freed with read. Okay. So you were not aware that malloc was made here because the function did it. So you absolutely need to know this because they're going to have to call it free after. Okay. It's just one of these things. So you might have memory leaks if you don't know how the functions here work. So just make sure to, if you are using them, just look at the manual and they're going to tell you if they are allocating memory or not. Okay. Okay, so those are still examples of dynamic vectors. So here we have a string copy. And does the string copy allocate memory? Blah, blah, blah. I think not. I don't see any mention of it. Okay, so this we covered. Create a struct of your choice. Okay, we're running out of time, so we'll skip that part of creating a struct of matrix and everything. But essentially what you're going to have to do, because it's a lot of hard manual work to allocate a struct, is you would just create yourself a function that would allocate a matrix, for example. So it's no different than any other function, at the exception that this function, for example, dynamic vector. So here I'm defining a function struct that returns a dynamic vector, and it's going to be alloc vector. Right? So here, and I'm going to pass it parameters such as int length, name. So it could be a const jar pointer, right? Name, and finally no data because it's going to be initialized, right? And then what I would do is just do what we did here, right? Like this. So creating this thing here, instead here I could have length right over here, and length again here. The name would be the name here. Okay. And finally I would return the D. Okay. So now I could have struct dynamic vector v2 equals malloc sorry, what's it called, alloc vector, and then I want a length of 200, a name of my tag, and finally, yeah, that's all I need really. Okay, so it's going to return by value a vector and not a pointer. Okay, but then if I created a function to create an alloc a new vector, one good practice would be to create a void function that would free vector. So by doing this, you ensure that you do this after defining your struct. You ensure that you will always like allocate it the correct way and free it the correct way. So instead of using free all the time, you do it once. So in our case, we only need to receive actually to receive a pointer. Yeah. So here you created the alloc matrix. And for the free matrix, I don't know if it did that. Okay. So here you would not okay. So we definitely need a pointer. So struct what's it called? Dynamic vector pointer to v, and it would be free v dot it was data, right? Free data. So let's hope this works. So I allocated it, and now I'm going to type free vector, and I'm going to pass the address in memory of v2. Okay. GCC3 memory.c. In function main, the undeclared. First use that function. Oh, right. I did. Where is it? Okay. Yeah. Just going to remove this old code here. Okay. Okay, do not name const from. Okay, it's just a warning. Okay, and as you can see here, there are still no leaks. Yeah, there are still no leaks. So I was able to allocate memory with my function alloc vector here, and free vector. So, you know, we say that C is pretty low level. It's okay. You don't have to work in the dirt. You can build some starter blocks from the ground up, but after that, just use your own functions. And this way, it's already, you know, at a higher level than what we did before. So free vectors and treat the vector properly. So if you are to make a struct for the page table, for example, it might have multiple pointers, multiple things. So you need create page, for example, the function create page table, or function create frame alloc if you create a new frame store. See that kind of things. So you might need to create functions like these to maintain like decent code. Okay. Okay. And some data, yeah. Structural parameters. Okay. So the exercises, I'll let that to yourself. So we can absolutely do structs and structs in the same way that do you guys know Java? Okay. In the same way that in Java you could have the class, I don't know, a class inside of class, right? Well, in Java everything is in a class. So the class animal is a child of the class object, and well, actually, this is heritage, so it's not the inheritance is not the same thing, but so let's say we're gonna create structs inside of structs, and this is where the free and the thing can get a bit tricky. Structs.c. Okay, so let's say I define a struct called page. Okay, page. So a page has what? An index. Okay. It has yeah, page index. And let's say the page points to int array of I don't know, lines 3, because your page in this assignment are like 3 lines of code long, so it would be lines index. Okay. So here I would store, for example, the index inside the frame store, but we don't care about that for now. It's just an abstraction. And okay, I'm just going to do that. If you try just doing that in your assignment, you're probably going to need a lot more variables, but this is just a basic example. And then I would like to have a PCB, okay? A struct PCB here, which is going to contain PID, okay? And also a struct, the struct page. Like this, okay? This way, okay? And let's do something else. Let's actually do this. So this is an, actually, length. Okay, so here I have a struct with an array of int represented by a pointer, and the length of this array is the length of this variable. So what's inside of that variable is going to tell me how long it is. So here I'm absolutely going to need to do a, what's it called? Malloc, right? But here, instead of passing it by here it would be passed by value, and by value I mean the PCB would literally copy the page, which is completely useless, because when you think about you want to point to a page table, you want to point to a page, so this absolutely needs to be a pointer, right? So we're going to have a pointer to that. I don't know where VS Code went. Okay. Okay, so in order for that to happen, I would first need to allocate a page and then allocate the line index. So a lot of threes and a lot of things here to do. Okay, so int main. Okay, we're gonna return 0 here. Okay. So the first thing I'm gonna do is the okay. The lowest level would be the page. Okay. So I'm going to create a function that's going to return a struct page. And alloc page. Okay. Alloc page or create page, for example. Okay. So I'm going to pass it, what's it called? The page index. Okay. So int page index, then the length, int length, and that's it. Okay. The rest is going to be allocated dynamically. So in here, I'm going to call it struct page, and we say p, okay. And then p dot length, p dot page index first is equal to page index. So this is fine. P dot length is equal to length. And finally, I'm going to do p dot what's it called? That would be the line, yeah, lines index. It's going to be a malloc of the size of, oops, size of an integer, because it's times the length, right? So we're allocating memory for that, and we're just going to return by value. So return the entire object we just created like this, okay? And then I have a page here. So let me create a page, and that will be page, yeah. Okay, struct page. P equals alloc page, page index, page index length, right? That works. Oh, sorry. I'm actually going to need, okay, so let's say the index of that page is 0, the length is 100. So it would be 100 lines of code. And then finally, I'm going to have a PCB created. So I'm going to create this in the same fashion, a PCB. Struct PCB. PCB, alloc PCB. And okay, so I would have the PID here, which is just something. And here it takes the struct page pointer. Okay, page. Perfect. So struct PCB again. So you get the idea. Struct PCB, I'll call it to return, to be clear. Okay, so to return dot PID. We already know it's the PID. And to return dot page is simply the page, right? And then we're going to return to return. Awesome. Okay. So I'll create now the what's it called? Struct PCB E equals alloc PCB. And then it's just the PID will be 2. And the page pointer will just be dereferencing the page that we defined over there. So great. So now, what happens if we, okay, we're gonna just try and run this, right? So GCC, what's it called? For structs. Okay. Structs, malloc string size of, okay. Yeah. What did I do wrong here? Size of int times length, p lines index. Implicit derivation of built-in function. Okay, I probably needed to add the input and std whatever here. Structs over there. Oops. Like this. Okay. And again, these are just warnings, so incompatible. I feel like I'm missing something. I just don't see it right now.
You're missing the log.
STD what? STD lib. Oh, okay. Oh, really? For malloc? Standard lib. Didn't I? Okay. Funny. Include std lib. It's kind of weird. Oops. Lib.h. Okay. GCC for structs. Okay, no warnings. That's a good thing. A dot out. Okay. Of course, I didn't do anything. So let's just run Valgrind here. And as you can see, we have the same problem with our structs, is that I allocated memory that I now need to free, right? And let's go a step further here. Okay. So I've defined it's just a pointer or reference to a variable that I created. But here I'm going to do something else. I'm going to do page pointer, and I'm going to do malloc, and then what's it called? The struct size of struct page. Okay, so now I will be dynamically creating a struct or allocating memory for a struct. Before that, it was just a local variable on the stack, so it was done at compile time. But now I just have a pointer for that page, okay? And of course, I'm going to need to initialize it. So This is the tricky part. So I guess I could have P equals, what's it called? Alloc page, yeah, alloc page, and then 0 and 100. Yeah. Does that work? Yeah, I'm not sure how this could work because here I return an object and not a pointer to an object. So it's a bit weird. Actually, yeah, I would have to redefine my function to take a pointer and allocate it, right? Because right now I'm returning an object, but I could create dynamic alloc page. I know I'm running a bit behind on time, but bear with me in a second. It's actually useful. So the struct page here, alloc page, we're just going to return void because we're not doing anything. And we're going to take a pointer to a page. So struct page pointer P, okay? And here what we do is just we replace that with small arrows. Well, where is everything? Okay, page index. Of course, we're going to do the page index, in page index, in length, right? Okay, so this works now. Length here. So we have a more complex setup here that right now is completely useless. You don't need to do that in this scenario, but it just in your assignment, you just might need to do something like that of creating dynamically a struct. Right now, I'm allocating it. I'm going to call it, you know, initialize point. Yeah, alloc page pointer, so that we're clear. Okay. And a lot of functions in C actually work like that. You pass a pointer to it and they do something. So here I would just have alloc page pointer, and I would have the pointer, of course, and then the page index, which would be 0, the length, which would be 100, and it returns void, so that's okay. And then P here. So what would that would that do the ampersand sign here in this case? Because I define the, a pointer here to a struct page. And I've allocated it. And here I didn't use anything, any symbol, but here I used, what does that do? Any idea? So this is the dereferencing. So here, by doing that, we get the address of whatever it is, okay? So this is a pointer, okay? So a pointer, it's just an address to the address of something else, okay? And this address was returned to us when we allocated memory, okay? When we do allocate memory, we get the pointer. So we say, hey, by the way, can I get 100 thing here? And they say, okay, by the way, it's at address 10, let's say. So this is where your 100 thing was reserved. And then by doing alloc page pointer here, and here, by the way, the value that's returned is the pointer. So here, P equals 10, okay? Alloc page 10 here. So replace with P by 10, and I'm just saying the function at address 10, do something here. And by doing that here, I'm saying, where's the address of the address? Okay. So it would find where in memory is stored the address of that. So it's like the address of the pointer itself. So yeah. So double quotes, so you don't need to do that, please don't. You just need to pass it. Actually, it depends. alloc PCB. The PCB is asking for, what is it asking for? Let's see, alloc PCB. Yeah, it's asking for a pointer to a page. We already have that. But before, it was not a pointer, it was just an object. So I was like saying, what's the address of that object? Okay. So let's do GCC struct.c. Node declared here, return with a value. Oh, returning void. Okay. I forgot something here. Oops. Alloc page pointer. That's actually not this one. This one, you know, it's void, so should not be returning the pointer. Okay, no warning. Okay. So here we have something interesting, which is, so before we only had one league, the 400 bytes in one block, but now we definitely lost 16 bytes in one block. And by 16 bytes, we're probably talking about all the pointers that we did, okay? So if we allocated something for the struct itself, okay? Turns out the struct was 16 bytes, okay? And indirectly, we also lost 400 bytes. By indirect, we mean it was inside the 16 bytes that we were pointing to something else. So it's indirect. So now all we need to do, and I'll wrap it up because I'm really running behind, is just free memory. Or perhaps I could let you do that as an exercise. So to free memory here, you would first have to free the very inside of it and then go outside. So if I have a PCB that contains a pointer that was mallocated, you would go to the pointer, and here the page, you would go to so you would go inside the page, you would free line index first, then you would free the page, and yeah, that's it. That's just 2 level deep, right? You would free, by freeing the page, I would mean free this, okay? So we did create a function, right, which was called free PCB, and it would free the page pointer. Where was it? Actually, I don't see it here, but that doesn't matter. So we would first, and that's the reason where you create a free function yourself, like void free page. So struct page pointer p, you would go into p dot, I do a dot, but it's probably going to be auto corrected to something else, p dot lines index, right? And we're going to free that. So you free this thing first, right? And then you free the pointer itself. Okay, so you free line index because it's something, and you free the pointer that you were given. Okay, so now I'm just gonna do free. What did I call that? Oh, just free. No, very bad idea. Free page. Free page. And then I'm just passing it a pointer. The pointer that I will be freeing memory from. Okay. And I do this after I'm done with the program. So hopefully it compiles, and if not, okay. Okay, so now everything has been freed. Okay, you're free to go. Do any of you have any questions? So just keep in mind that it's perfectly fine to nest functions of structs inside of structs, but the moment you have memory, every time you're doing a pointer in that memory, immediately call a free function or define your own free function to never forget it afterward, okay? Because otherwise it gets really complicated. And like I said, the auto reader will include that ball writing and we'll check for memory leaks. Okay, so very important to do it. It's also much easier to debug. All right. Thank you guys.
You know, they check for memory leaks.
We did not. I could have thought about it, but I thought about it in assignment 2. So we'll not check for memory leaks for assignment 1, but you were lucky because